Hello, and welcome to our next set of college algebra notes. We're starting Unit 2, so our first section of Unit 2. We're going to start off with something a little different. We're going to start off with complex numbers. You've probably heard about these talked before, imaginary numbers. So we're going to talk about those. That's the first thing we're going to hit in this section. So complex numbers, it's one of those names that's not a very good name because it makes it sound a lot worse than it is. So let's talk about first off, what are complex numbers? What are imaginary numbers? Where did this all come from? So in mathematics, we present problems, usually as equations, and then we try to solve them. And hundreds of years ago, mathematicians were presenting problems, and they came across a problem that looked like this, where they had something squared plus 1 equals 0. And they presented it, and people looked at it and said, wait, you can't solve this. Because to solve this, you'd have to have something that you've squared, means multiply it times itself, and you get a -1 because -1 plus 1 is 0. So we'd have to have something squared that gives you a -1, but that doesn't happen because when you square something, you multiply it times itself. And if you take a positive times a positive, because if you multiply positive times itself, you get a positive, not a -1. If you take a negative times a negative, you also get a positive. So no matter what I pick for x, this wouldn't work. There's no solution to this equation. And not only is there no solution to this equation, there's a whole bunch of equations to write, infinitely many equations you can write that are like this, where you end up having to square something and get a negative number in order to be able to solve the equation. And originally, people just looked at an equation like this and said, oh, there's just no solution. You just can't find an answer. Now, some mathematicians try and look at things from a different perspective. And eventually, a mathematician came along and said, hey, I'm going to kind of come up with this idea that I have something, if I square it, it gives me -1. And then I want to see where that goes. I just want to see what that lets me do. And so he started solving these problems using this one term that, when you square it, you get -1. And it was really amazing because it let him do all kinds of problems that before you couldn't solve. There's, tons and tons of problems. In fact, eventually they figured out that basically any problem that can be written as a nice little equation like this can be solved now if you let him just introduce this one new value that if you square it, you get -1. And at first, the other mathematicians looked at him and said, you're crazy. You can't square and get -1. So that's just silly. You're just being goofy. You made up this imaginary number, and then you tried to solve problems with it. But his imaginary number had worth. It had value because it let us solve problems we couldn't solve before. It actually came into real-world situations. There were real-world problems that we weren't able to solve until we introduced this idea, this concept that this mathematician had, and started using this to solve problems. So even though it's not a real value, there is no real thing that you can square and get a negative, having a value that we can use in mathematics that does that is actually really valuable. It actually lets us solve real-life problems. So we do have a term, and because of originally other people making fun of it, the term is called the imaginary number or the imaginary unit, and it is I. I stands for imaginary number, and it is the thing that when you square it, you get -1. So if you take I and you square it, you get -1. Well, what is that? Well, this value then is something that is equal to the thing that times itself gives you -1. So another way of thinking of this is that I is the square root of -1. I is the square root of -1. Remember, square root says what times itself gives you this value. So I is the thing that if you multiply it with itself, if you square it, you get the thing inside there. You get the -1. You can see here if you square root both sides, the square would cancel and you get square root of -1. Or if you take the bottom and square both sides, you get I squared, and here you get -1. So I is this value. I is the square root of -1. There's no real life analog to this. We can't look at a real life example and say, here, this is the thing that does this. And so it makes it feel really weird. But mathematics is more about solving problems than it is about having everything in mathematics correspond to something that we know and understand in our real life, something that we can get a really concrete example of. And this I does let us solve all kinds of problems. I actually took a class, an entire semester, dealing with how to, using complex numbers. They called it complex analysis when I was in grad school. And half the class was computer science majors, because those computer science majors would actually use imaginary numbers, complex numbers, to solve problems when they're developing their programs and stuff when they work with computers. There's also heavy usage of I in engineering. So if you get to like electrical engineering, there's a lot of I in that. A lot of people use complex or imaginary numbers. So this is actually something that's ubiquitous throughout higher level mathematics and engineering. So we're stuck with it. And we're stuck with the name too. We're stuck with the name imaginary number just because back in the day someone thought it was a weird concept, a funky idea. But we use it now. So now I is the solution to problems like this. If I take I and I square it, I get -1. And so I can do -1 plus 1 gets 0. So I is this number. Now, first thing, there's this kind of weird pattern that happens when you take I to various powers. So if you start off with just plain old I, right? Plain old I is the square root of -1, just I. Then you take I and you square it, and we already saw that when you square I, you get -1, right? That's what happens because I times itself gives you -1. The square root, when you square root, you get the stuff inside, so you get -1. But then you take it and you take it times another I. So instead of I to the second, you do I to the third. Well, what do you get? Well, if you take I times I squared, you're taking I times -1, and you get a -I. Sorry, -I. I forgot the dot on my I. So -I. Next thing you do is, what if I multiply that by another I? So I get I to the fourth. Well, then if you have -I times I, because you multiply by another I, then you end up with an I squared again. So you end up with another -1, but it was already negative. So it actually ends up being a +1. And so this kind of happens where you start off with I being the square root of -1, but if you multiply I times itself, you get -1. If you multiply by another I, you get -I. If you multiply by another I, you get 1. And then if you multiply 1 times anything, you get that thing and get it back. So when we go and we multiply by one more I, when we do I to the fifth, we end up with I. And we're back where we started with, regular I. So now if I do I to the sixth, I'm going to be back at -1. See how if you take I to the fifth times another I, that's the same thing as just taking I times another I, and you get I squared, which is again -1. If I multiply by another I to the seventh gives me -I again. If I multiply by another I, I'm back at the same thing as I got with the I to the fourth. When I do I to the eighth, I get +1. And we call this the circle of i's. So the circle of i's, because it makes this kind of circle where it just kind of repeats, right? You do start with I, -1, -I, 1, and then you go back again. I, -1, -I, 1, and so on and so forth. So if we kept going, like I to the ninth, we'd be back again. 1 times I would give us another I. And we'd be back at the I again. Now, this circle of i's actually makes it so that we can calculate I to basically any power pretty easily. So I can pick a number like I to the 27th. I to the 27th. And you could sit there and count out this pattern until you get to 27, but that's going to be a while and that's kind of painful. So instead, the trick here is noticing that after every 4, you start over again. So what we do is we take the power of 27, and we divide by 4 and figure out how many times does 4 go in there, because every time 4 goes in there, we're back to 1, and we start over again. Well, 4 goes into 27, what is it, 24, so it goes in there 6 times? It goes in there 6 times, right? So 6 times with a remainder, because 4 doesn't go into 27 evenly, so it goes in there 6 times, yeah, it gives you 24, and there's 3 left over, so with a remainder of 3. So what this lets us do is say, okay, well, every 4 times, we're just back to the beginning. So 4, 8, 12, 16, 20, 24, we're still at 1. And then when we hit 25, we'd be back at I. 26 would be at I squared. 27, or the remainder 3, tells us that we're actually going to get a -I. So because of the remainder 3, this guy right here tells us that the answer to this is -I. That's because the remainder was 3. And this is our 3. If you got a remainder of 2, you would have got a -1. If you had a remainder of 1, you'd be at this I, the original I. If you had a remainder of 4, well, you wouldn't have a remainder of 4 because divided by 4, you get 0 remainder. You'd actually be at this one because there's no remainder of 4 when you divide by 4. So you get 1, 2, 3, and then this is actually our 0. Because if it divides evenly by 4, you're on this column. So that's the idea. You can take any I to any power, divide by 4, and just do remainder division like we did in grade school. And then this number at the end, 1, 2, 3, or 0. So this would be the 0, 3, 2, and 1. That'll tell you which result you get. Do you get I, -1, -I, or 1? That's how that works. Just a quick kind of silly little thing. We're not going to really use that throughout the semester. It shows up in the homework, so I want to make sure I showed it to you. And it's kind of an interesting little thing, but it's not really going to show up past this homework. So don't worry about this for like the exam or anything. We won't cover that. Now, I talked about complex numbers, but I started off with the imaginary number. Now, what is complex numbers? Well, complex numbers are just when you take the imaginary number and combine it with other real numbers. So I is the imaginary number. I is the imaginary number. That's why we use I to stand for it. But complex numbers are just a compounding or a combining of I with other numbers. So you can do things like you can take I and you can add 2 to it. So you end up with 2 plus I. We always like to write complex numbers, which have a I part and then a non-I part, with the non-I, the real part, first, and the I part second. So this would be a complex number. It's 2 plus I. Now, we can't really say that any better because we don't know exactly what I is. Like I said, there's no real example of what I is. So we know I is a number. We can use it. It works to solve problems, but we don't know what it is, so we can't really say how you would add I plus some real number. There's just no way to do this. And that sounds weird, but then you stop and think about things like the square root of 2. Square root of 2 is a real number. It's the number times itself that gives you 2. But there's no better way to write it than like the square root symbol 2. And so if I wanted to add 2 to that, I'd end up with kind of the same thing, 2 plus the square root of 2. Or if you had like pi. Pi is a number that goes on forever. There's no nice way to write it except for the little pi symbol. 2 plus pi, you just write the same thing. So this is what we do with I. We just write it like this. Now, you can do more than just add. You can multiply. So I could have a number like 5i, where I multiplied 5 times I. That's a complex number. This one doesn't really have a real part because we know when we multiply stuff together, it combines it together. So this 5i is going to be kind of the imaginary part. We have 5 of these i's, right? When you multiply, it's like you have 5 of that. There's no real part here. You can think of the real part as 0. But this is a complex number because it's got an imaginary part with other stuff going on. Complex numbers includes all numbers that have i's and all numbers that don't have i's. Once we basically throw it all together, that's what we call complex numbers. You could take I and you could multiply by a fraction. You can multiply by like a third. So you could have 1/3 times I, which you'd write I over 3 a lot of the times. That's how a lot of people write that because it's like 1/3 times I. But you could also take that and add a number. So let's say you add 7. So you end up with plus 7. And that would be another complex number because it's I, where you took I times 1/3 and then added 7. And that's a complex number with real part, imaginary part. Now, my math lab doesn't like it when you write complex numbers like this. So just to be heads up, when you write a number in my math lab, they want you to write it like this, 7 plus 1/3 I. And that's the preferred for my math lab. They prefer them written like this. They always like I on the side with the number part here that's not the I on the side. So even though you could just multiply 1 times I and get the I on the top like this, they prefer it written like this. So this is for my lab. Just a heads up for you when you're doing your homework. If you write it like this, my lab might count it wrong. So you want to put that on the side. I have no problem with this. If this is a test you're going to show your question, you can totally write it like this. I'm going to completely accept that because that to me is fine. 1 times I is I, so this is okay. You can have other roots in a complex number. So you might have a complex number where you add like the square root of 3 plus square root of 2 times I. So we took I multiplied by the square root of 2 and added the square root of 3. You'll notice here I put the I on the left side. This is just something we do to be careful because we don't want people to think this I is underneath the root. I put these weird little hangers on my roots just because that kind of tells people that's where it stops. But some people don't, and so they'll put an I on the side and it'll look like it's inside the root. So a lot of people by default kind of put it on the left side just to kind of save people thinking the I is inside the root. Because I actually has a root itself, right? I is square root of negative 1. We don't want a double root because you put an I inside another root, it's like a double root, and that's not cool. So these would all be considered complex numbers. Again, they have an imaginary part. And again, like I said, complex numbers really just is all numbers, including i's. Most of the time in math, people would work with just real numbers and they kind of ignore the i's. Complex numbers means we're going to work with all the real numbers plus all the imaginary numbers. And that's why it's called complex, because you're adding stuff to it. It's not just the real numbers, it's also the imaginary numbers. Again, it's a name that's stuck. It makes it kind of sound terrible, like, oh no, it's really confusing, it's complex numbers. It's a little more than just real numbers, so I think it kind of makes sense a little bit, but it's not as bad as it sounds. And again, standard form, we always put the real part first and the imaginary part second. If you put I plus 2 instead of 2 plus I into my lab, that's going to count it wrong. And we do the same thing on test, because I'll put on my test, I'll remind you that you want to write it this way. That's the way we always write complex numbers, with the real part first and the imaginary part second. Makes it simple. Okay, now where does this come from? How do these i's show up when we're doing problems? Well, one way is you'll be working with problems and you'll end up with a negative in the square root. Now, previous in the semester, unit 1, if we saw something like this, we would have just said, oh, I can't do that. There's no such thing as a square root of a negative number. You'd say you can't square root negative 16. Well, now, because we're going to work with I, we can actually work with something like square root of negative 16. What we'll do We're going to break it up. We're going to break it up into the real part, the square root of 16 that you can actually solve, and then we're going to break off the -1, the negative part that will turn into an I. So we'll take things like this and we'll always break it up into the real part. So I'm going to do the square root of 16. And the imaginary part is going to be the square root of -1. We can do this because there's a rule about roots that you can break it up by multiplication. So we're going to break this into multiplication. We have square root of 16 and the square root of -1, because 16 times -1 gives me -16. Now, square root of 16, that's easy. We just do that, we get 4, right? Square root of 16, that's what times itself gives you 16. The answer is 4. Square root of -1, remember, square root of -1 is I. That's the definition. That's what I is. I is the thing you multiply itself gives you -1. That's what this root means. Root says what times itself gives you -1. Well, I is the thing that times itself gives you -1. So this becomes I. So we get 4 times I, or just we write that as 4I. Because if you put number next to a letter, it means multiplication. So that's it. That'd be the answer for that problem. If I took this and wanted to write it as an I, I'd write it like this. Same thing with square root of -5. Now this one, again, we're going to break it up into 2 parts. This one, square root of 5 doesn't solve nicely. We can't square root that. So I'm going to go ahead and leave it as a square root. Square root of 16, we could solve it and go like that. But square root of 5, we can't. So we're just going to leave that square root of 5. But again, we're going to pull the negative out of here. Pull out the negative, so we get -1. And again, -1 times 5 would give me -5. So I'm breaking it up by multiplication. And I'm just taking this square root of -1 part, saying that that is I. So this is I times the square root of 5. And again, I can't multiply that. I don't want to multiply that in because the I is on the outside. I broke it up like that. I want to leave it like this. But I'm writing this to show that it is multiplied. I times this number. And that'd be that part. Again, I like to put the I on the left, not on the right, just so people know it's not inside the root. That's how I'd write that answer. Let's try another one. This one's got a negative outside and a negative inside. Sounds kind of crazy, but it's not as bad as it looks. First thing, again, I'm going to do, I'm going to break up the negative and the number. So we'll break this up into root 12 and the root -1. Because anytime you see a negative inside the root, the first thing you should always do is pull that -1 off of it and just work with the positive number. We don't like to try and take the roots of negatives, so we just break it off into a -1 because we know that just becomes our I. And that's what we'll do with it. We'll say, okay, if I can pull the negative out of there, that gives me an I, and then I can just work with what's left. Now this one is one of those roots where it doesn't solve. If you try and square root 12, you get some decimal number. If you throw it in a calculator or something like that, it goes on forever. It's not a nice decimal. So instead, what we do with this one is we're actually going to simplify it. So here we're going to simplify the root. Remember that when you simplify roots, what you're doing, you actually break the root 12 into 2 parts, the part you can square root and the part you can't. So we square root 12, we break it into square root of 4 and square root of 3. Because 4 is a nice number, it's a perfect square. So I always want to look for things like 4, 9, 16, 25, 36, the things that will come out of the number that will square root. 4 is 2 times 2, so we can square root 4, we just get a 2. And then whatever we pull out, we look at what's left over, and that's just going to be still inside the root. So we can't square root 3, right? It's just leftovers, so we leave it inside the root. So something like root 12 should simplify to root 3. It's something we've done before, but just a good reminder how to simplify. Again, you always think about what can I pull out of this number that will square root. And that's the part you get to square root. And what's left over will just stay inside the root. So this becomes 2 root 3, and then don't forget to bring down the negative as we go. So there's still that negative on the outside. The last thing when I'm writing this, I would actually put it like this. I would put -2I root 3. You have to be too careful, because if you write it like this, it's not wrong. And I would totally accept it like this. My lab would accept it like this. This is just safer again, so I tend to write it like this, because then people don't think my I is inside the root. So you'll see me do this throughout the semester. If I work with the I's, I'll kind of put them before the root and after the whole numbers. You could put it in the front, you could put it in the back. It's not wrong in any of those locations. It's just kind of safer here. It makes avoids mistakes, and that's why mathematicians have gotten this habit of putting it in the middle like that. All right, do one more. This one, again, I want to write this with I's, so I'm going to take this 9, I'm going to break it down. Again, I'm going to break it into the 9 part and the -1 part. I'm still square rooting both parts because it's a square root, but breaking it up into multiplication, so I'm doing the whole thing at once. 9 I can square root, so I just get a 3. -1 I can't, but I can rewrite this as I, because again, square root of -1 is I. And just bring down this 3 that they were adding at the front, and that's our answer. Again, the real part always goes in the front, imaginary part on the end. So not a lot of these have both parts, but this one does, so I want to make sure we put that real part in the front. Again, that's the A plus BI form. So if you put the 3 on the back on this one, plus 3 on the right side, that would be wrong because they want standard form for all your imaginary numbers. This stuff where there's only one part because it's all multiplication, that's just the imaginary part, so it's all done. Same thing here and here. We'd have to worry about order because there wasn't a real part to add to the imaginary part. Okay, so that's kind of getting an idea of how we see i's, where they come from and stuff. Now, one thing you'll see and you'll do with i's this semester is you'll take those numbers, complex numbers that have i's in them, and you'll add, subtract, multiply, and divide. So that's going to be basically the rest of this section, is we're going to take these complex numbers and we're going to show what happens when you add them, subtract them, what happens when you multiply them, and how you divide them. So that's what we're going to go through for the rest. So first off, I want to add and subtract complex numbers. Now, it sounds scary, but it's actually not that bad because it's really familiar. This is going to work a lot like how when we add numbers, polynomials with x's in them. So I have here 5 minus 11i and 7 plus 4i. Well, if this was 5 minus 11x and 7 plus 4x, and we wanted to put those together, we'd do that by adding the like terms, right? We'd take the 5 and the 7, because they don't have an x, and put them together. And if this is 11x and 4x, we'd put those together, minus 11 plus 4. Well, this is going to work the same way for i's. You can almost think of them as like terms. I know they're not quite like terms because there's no x's there, but they kind of are like terms. We're going to add the reals plus the reals, and we're going to add the imaginary plus the imaginary. So we're going to take the real components, 5 and 7, and add those together. 5 plus 7 gives me 12. We're going to take the imaginary components, the minus 11i and the plus 4i, and put those together. Well, negative 11 plus 4 still gives you a negative 7, so we end up with a minus 7i. And that's how we do it. That's it. That's adding complex numbers. It's really not that big a deal because you just match the real parts, match the imaginary parts, put them together. Watch the signs. Be careful of your signs so you get the right sign when you're done. Always real part on the left, so that's why I did the real part first, and imaginary part on the right, because that's why I did it second. So when I do it, get an answer like that. So that's adding. That's it. So pretty easy example. So that's what you do. Now, subtracting, you got to be a little more careful. One of the big mistakes that happens, what I see is I see people start subtracting, and they do like negative 2 minus 8, and they get that right because they get negative 10. And then they do 3i plus 6i because they forget about the minus. It's so easy when you're doing a problem like this to do half of it and forget about the minus halfway through. So what I do is I never actually subtract these. I don't ever subtract complex numbers. I always turn it into addition. You're allowed to change a subtraction to addition if you change the sign on the second part. It's kind of the idea that you can subtract 5 or you can add a negative 5. Either way, you're going down. Your money level is going down. If I take $5 or if I tell you you owe me $5, either way, you're going down. So I'm going to turn this to addition, and I'm allowed to do that as long as I change these, both of them, into negatives. So we turn it into addition. Turn it into adding a negative. And that's why we're allowed to do this, why we can change to addition, because we're adding a negative, same thing as subtracting. Now that I can just think of it as addition, it makes it a little bit easier. So I can just think about negative 2 plus negative 8. So negative 2 plus negative 8, which is negative 10. 3i plus negative 6i. So 3i plus negative 6i. Well, 3 minus 6 or plus a negative 6. Either way, you get minus 3, and don't forget the I. And it kind of keeps the label, right? The I, just like when we were doing x's, you keep the x. So that is our answer. So subtracting, not too big a deal because you can just turn it into addition. Change the sign here, but make sure you change all the signs on the second part. Don't change the signs on the first part, just the second part. So that's adding, subtracting. We're not going to do a whole lot with those, but if you ever have to, now you know what to do. Add like terms, or the matching parts. Next thing to deal with is multiplying. So we're going to do a couple different multiplying problems. First one I want to show you, notice this one has these square roots instead of i's. So I just want to show you that if you're multiplying with square roots, one thing you got to be careful about if you have negatives inside your square roots is you do need to pull out the i's first. If you try and do this problem right now and multiply negative 9 times negative 16, you actually get the wrong answer. You can't do that. It'll give you the wrong answer. So instead, what we have to do is first thing, we have to break these up so that it becomes the square root of 9 times the square root of negative 1 and the square root of 16 times the square root of negative 1. So we're breaking this up and turning it into the component parts because first thing we want to do is get the i's out. And again, remember that I is the square root of negative 1. I should put my equals more space. So I is equal to the square root of negative 1. So square root of negative 1 becomes an I on both of these. And then these root parts are pretty easy. Square root of 9 is just what times itself gives you 9, so that's just 3. And root 16, that's what times itself gives you 15, that's 4. So we end up with 3i times 4i. Now we can multiply the numbers, 3 times 4, you get 12. And we can do I times I. Well, that's just squaring, right? Because I times itself is squaring. So we end up with I squared. And we already talked about the fact that I squared, remember that I squared, is negative 1. Because if you square both sides, you get negative 1. So I squared is negative 1. That's one thing that's really different about I squared versus x's. You take x and you square it, and you get x squared. That doesn't change, that doesn't solve. But you take I and you square it, and you always have to remember that, because it gives you a negative 1. I is the number that if you square it, you get a negative 1. So anytime you see an I squared, you should go, oh, I squared, that's going to become a negative 1. So this becomes 12 times negative 1, because it's times here still, right? Always times. And when you multiply positive times negative, you get a negative, so this is negative 12. Now, if you were one of those people that multiplied first before you tried to break it up, you'd end up with negative 9 times negative 16. Well, negative times negative is positive. I think that gives you what? 90 plus 54, 144. And the square root of 144 is just 12, but it would be missing the negative. And that's why we had to do it this way, because those negatives here don't just cancel, they actually make the answer negative at the end. So that's actually the final answer. So back in the day before they had i's, they couldn't solve a problem like this properly because they didn't have i's. So now we have i's, we can actually solve this problem. Okay, let's try another one. This one, we got our i's out already, they're already there. Now I want to multiply. Now notice there's parentheses here, so as soon as you see parentheses like this, you should think distribute, right? Whenever you have multiplication with the parentheses, you should always think about distributing. So distribute the 4i to both parts like this, and multiplying 4i to the first part, 4i to the second part to get my answer. So 4i times 9 gives me 36i, because 4 times 9 is 36, don't forget the i. And 4i times 2i, 4 times 2 gives me 8i squared. So I get 8i squared, plus in the middle still. And again, we just talked about this, I squared actually turns this into a negative 1. Now, something I see a lot, one of the mistakes I see a lot, is I see people get a negative 1 here and think that the answer is 7. And it's because they forget that what we're actually doing here is multiplication, right? Whenever you have a number next to a letter, it's multiplying. So when this becomes a negative 1, it's actually 8 times negative 1, not minus 1. It's 8 times negative 1. That's why this becomes minus 8, because the negative 1 times 8 is a negative, or minus 8. The 36i will bring it down, because that just comes down. And so that's what we get, except this is wrong. Hopefully you notice that if you put this in my math app, that's going to count it wrong, because this is not in the proper standard form. Remember standard form, a plus bi, we always put the real part first, the imaginary part second. So we'd rewrite this as negative 8, and since this is a positive 36, we'll put positive 36i. There's no negative on it, so that's why I put plus in the middle. The minus has to stay with the 8, because the 8 has the negative. And that's actually the proper answer. This would be a wrong answer, because it's not in standard form. You always have to have that standard form. One of those fun things about this section is people will do the homework and they do all the problems right, except for they might not put it in the standard form, and that'll get you. So you gotta make sure when you're answering your questions in the section, always write it in that standard form. So that's why I make a big deal about that. That was a pretty simple multiplication with i's, because there was only one part on the first part. There was only the I part. Most of the time when you multiply complex numbers, they're going to have both a real part and an imaginary part. Like this one has real and imaginary. But that's actually not that big a deal, because you already have a method for multiplying these. It's called FOIL. Hopefully you recognize FOIL. FOIL is when we take 2 parts times 2 parts and we multiply it out. And it's just a way to remember to multiply this part to both of these and this part to both of these. That's all it is. So like I remember that I need to take first 2 times 1. So I multiply that first. 2 times 1 gives me 2. And I do my outer, so that's the outside parts, so the 2 and the 5i. So I multiply 2 times 5 and I get 10i. And don't forget the sign. 2 times a negative 5 gives me a negative 10. Then I do my inner. So inner is the inside 2 parts. So I get negative 3i times 1. Well, 1 just keeps it the same, so I'm going to get minus 3i. The negative 3i still. And then last, I'm going to take the negative 3i times the negative 5i. Well, negative gives me a positive, right? Double negative makes a positive. 3 times 5 gives me 15. And I times I gives me I squared. So I've multiplied it, but I'm not done yet because I do need to get this in standard form. So I'm going to have to do some simplifying. First off, those middle i's, they do combine. And then you'll see that all the time where you get 2 parts in the middle of their i's and you just combine them together. So negative 10 plus a negative 3, combine that, you get minus 13i. No big deal. Over here, we got that I squared. Remember again, I squared is negative 1. So as soon as you see an I squared, you think, okay, this will become negative 1. We do 15 times negative 1. And you'll notice after you've done this a few times that this I squared, really all it ends up doing, because you're multiplying by negative 1, is just changing the sign. So instead of a positive 15, we're going to end up with a minus 15, because a negative 1 here times 15 will make it negative. We've got the 2 on the front. The last thing, I want to subtract the outside parts, because now these are like terms. They're both real. So I'm going to do 2 minus 15, so I get a negative 13 from those. Still have the minus 13i, because that's the imaginary part, and that's my final answer. And again, real part first, imaginary part second. So that's what an answer looks like. And this is why standard form is what it is. Standard form has a real part and imaginary part, because no matter what you do with complex numbers, you always get a complex number answer that you can write in this way, where you can write a real part at the beginning and an imaginary part at the end, where you can write it into those two parts. You just put all the stuff with i's at the end and all the stuff without i's at the beginning, no matter what it is. And that's how come I always write in that standard form, real part plus imaginary part. Okay, I'm going to do a couple more multiplication problems, and then we'll talk about division. So first, what I want to do is actually multiplication, because it's squaring. This is where you take the quantity times itself, right? That's what the square says. Now, sometimes people try and get fancy, and they try and just take the square and square both parts. They try to do like 5 squared is 25, 11 squared is 121, and just call it done. That doesn't work. There are times when you can square all the parts, but that's when you have multiplication or division. When you have subtraction or addition inside of parentheses, you cannot square both parts. It's one of the most common college algebra mistakes ever. I've actually seen memes, like intermittent memes, about this mistake. Now, of course, I've got like math friends on Facebook and stuff, because I'm old, and they make those kind of jokes and stuff. But it's a common thing that teachers, joke about, or even students that have gotten used to it, figured out the idea, is that this common mistake where people try and square both parts, and it doesn't work. You don't get the right answer. You cannot square both parts because you won't get a full answer. So what you actually have to do is you have to take this and write it as a multiplication. Remember, a square means just take this whole thing times itself. So I'm going to do 5 minus 11i times 5 minus 11i. I'm going to write it out like that. And we're going to end up doing another FOIL problem. So that's what you actually have to do. To get the right answer, you actually have to FOIL this out. So I'm going to do my first. I'm going to do 5 times 5. And you do get a 25. And that's why people start to think that you can just square both parts. But we're not done yet. We've got to keep going, because the next thing is to do outer. We do 5 times a negative 11i. And we get a minus 55i, which is not part of what you get if you square both parts. So that's why we know that's not right. Next thing you're going to do is you're going to do inside. You're going to do inner parts. So to the negative 11i times 5, which actually gives you another negative 55i. So again, part of the thing that you would not get if you did it the wrong way. Last thing we're going to do that last part. So I'm going to do a negative 11 times negative 11. Well, negative makes a positive. 11 times 11 is 121. And I squared is, I times I is I squared. We know that I squared is negative 1, so we'll do that in a second. But now you see there's actually more than just two parts. You can't just square both parts. You don't get the right answer, because these middle two parts, they stay there. They're not going away anywhere. They stay there. What you end up doing is you actually add those together, right? A negative 55 plus another negative 55, you end up with a negative 110. 50 plus 50 is 100, 5 plus 5 is 10, and they both have i's, so I end up having an I. So that's why we can't just square both parts. You miss this middle part you're supposed to have. On the right side, remember the I squared becomes negative 1, so this actually just becomes a minus 121, right? Because we have the I squared becomes a negative, so it changes the sign, and we still have 25 at the beginning. Last thing, we'll combine those real parts. 25 minus 121, I think that gives me negative 96, if I think about that right. Yeah, so 21, and then 4 left over, yeah, so. And then over here we got a minus 110i. And that's our answer for this one. So our answer for this one is negative 96 minus 110i. And that's what we get from that. Okay, so if you see a square, don't just square both parts. You can't do that. That's not how it works. You multiply it with itself. You do a FOIL problem, and you get an answer. Okay, I want to show you one more multiplication. This is another kind of weird one. This one you'll notice is similar, where they almost look like they match, right? 2 minus 5i, 2 plus 5i, they both have a 2 and a 5i. The only difference here is now the signs don't match. We have a name for this. In math, we call these conjugates. So a conjugate, the only difference is the signs. They're conjugates because the signs are different. Everything else is the same, and that's what makes them conjugates. So they have to be conjugate. They have to have the numbers be the same, but only the signs are different. Only the signs are different. And that's what makes it a conjugate. Now, something happens when you multiply conjugates. It's kind of interesting, so that's why I want to show you a different. Sorry, trying to talk and spell at the same time is not always a fun thing. So when you multiply two conjugates, something weird happens. Now you do this with FOIL still, so I'm going to go ahead and still FOIL this. I do 2 times 2, and I get 4. Do my outside, I do 2 times positive 5i, and I get a positive 10i. Do my inside, negative 5i times 2, I got a negative 10i. And then we do the last, negative 5 times positive 5. Well, negative times a positive is a negative. 5 times 5 is 25. And I times I is I squared. And you notice that when you do this, the middle two terms are opposites, right? These two don't match. And if that happens, then, well, of course, they're going to cancel, right? Positive 10, negative 10, add up to 0. And the I squared over here turns this into a positive 25. Because, again, I squared is negative 1. Did I say that enough times? You know, I'm writing it down a bunch of times. I really want you to get this. I can't tell you how many tests I've gotten back where someone just left something as an I squared. And so I know they didn't know that I squared is a negative 1. You should know that. You know, you should know that as soon as you take I and you square it, you get a negative 1. Okay, over here I still have the 4, so I'm going to write the 4 down. And I'm down to numbers that don't have any i's. And that's what's special. If you take a number and its conjugate and you multiply them together, if you take two conjugates and you multiply them together, you always end up with something that becomes real. 4 plus 25 just gives me a plain old 29 with no imaginary part. So I mentioned earlier how engineers can use imaginary numbers. And you're like, how can they use imaginary numbers? And how is the electrical engineer going to sit there and tell me how much foot of cabling I need for this, you know, electrical device if they have to use i's? Well, they don't have to use i's because when they want to, they can take and they can multiply by a conjugate. And those imaginary numbers turn back into real numbers. So they can solve this problem using complex numbers, and then when they're all done and they want to go back to real land, the land where the numbers are real, they multiply by the conjugate and they're back to using real numbers, and they can tell you how many feet that cable needs to be, or inches, or whatever it is. And so that's the idea. That's why we can still work with imaginary numbers even in like real world problems. Okay, that's multiplication. So multiplication, you'll notice, is mostly just FOIL, right? It's a lot of FOIL. The only time it was really two different is when we had, you know, a number of times 2 parts like this where you might just distribute, which is even easier. So that's pretty cool. But most of the time, multiplication is just FOIL. So you should know how to multiply these complex numbers. That's going to be a great kind of show your work problem. So you should be ready for multiplication, or you should be ready for division. Probably should be ready for both. Because, you know, you'll see what, you know, they're both in the practice exam. You never know which one to put on the actual exam. Okay, I want to divide complex numbers now. So that's the next thing to do. Now, division with complex numbers gets a little weird. Now, multiplication kind of makes sense because you just multiply this times that and it works. Division gets weird because when you think about division, you usually think about in the grade school, like how many times does this number fit into that? You know, 10 divided by 2, well, 2 fits in 10 5 times. But that gets hard to say when I say something like 5 divided by 2 plus 3i. And then you have to try and think about like how many times does 2 plus 3i fit into 5? And that sounds like nonsense, right? It doesn't make any sense. So we don't really try and divide like that because that just doesn't make sense. It's not intuitive at all. It doesn't really make sense. So instead, what we do is we take complex numbers like this where they're divided, and we just say, okay, if I can get the I out of the bottom, if I get so the bottom does not have an I, then I can actually probably divide because I'll have numbers that are real to divide by, and then actually the division will be easy to do. So the trick here is to get rid of the I in the bottom. You start to think, okay, well, how can I make the I in the bottom go away? Well, we just talked about that, right? We said that the complex conjugates are these things where if you multiply by the complex conjugate, you can make the I go away. So that's what we'll do. Whenever you're dividing complex numbers, what we're actually going to do is we're going to multiply by the conjugate of the denominator. Remember, the denominator is just a fancy math speak for the bottom of the fraction. So we're going to look at the bottom of the fraction. We're going to look at what that imaginary number is there on the bottom, and we're going to multiply by its conjugate. So like in this case, the number on the bottom is 2 plus 3i. Well, the conjugate's the same thing with just a different sign. So the conjugate is going to be 2 minus 3i. So we're going to multiply by that. We're going to multiply that way. Now, you know with fractions, though, you can't just multiply the bottom willy-nilly, right? You can't just take a fraction and say, I'm going to multiply the bottom. You have to do it to both the top and the bottom. You know, it's like when you take 1/2 and you double the top and the bottom. You get 2/4. It's still the same fraction, right? Because 2/4 and 1/2, they both mean a half. 2 out of 4, 1 out of 2, they're both a half. It's the same idea here. I can multiply the bottom only if I also multiply the top. And so that's what we're going to do. we're going to get rid of the I in the bottom, but we'll end up putting the I in the top. And that sounds terrible, but it actually works out really well, because as soon as we get the bottom to be just a nice whole, regular number, no imaginary parts, just a real number, the division will actually work out okay. So that's the idea. We'll always multiply both the top and the bottom by the conjugate of the bottom. That's what we're multiplying by. And again, the conjugate, the only difference is the middle sign change. You never change the sign at the front, right? The 2 at the front, it's going to stay the same. It's only the sign in the middle that changes. From the top here, to multiply these, I would go ahead and distribute, right? Because there's just 1 5 there to multiply to both parts. So I do 5 times 2, I get 10. 5 times negative 3 gives me a negative 15, right? 3 times 5 is 15. And don't forget the I. On the bottom, we get to FOIL again. Did you notice we're going to do lots of foiling in this section? Yeah, we get to do lots of foiling. Okay, so we did 2 times 2, we get 4. We do the outside, 2 times negative 3i, which gives us a negative 6i. We do the inside, 3i times 2, and we got positive 6i. And we do the last, 3i times negative 3i. Well, 3 times 3 is 9, but positive times negative is a negative, and I times I is I squared. Now, because we multiply conjugates, we're going to see that those middle terms, again, cancel. And that'll always happen when you're doing these division problems, you're multiplying by conjugates. Those should cancel. If it doesn't, you messed up. That's a good sign that you need to go back and fix it. And then the I squared, of course, turns into a negative 1, right? I'll say it one more time. I squared is negative 1, so this becomes a negative 1. And a negative 9 times a negative 1 is a positive 9. So on the bottom, we get 4 plus 9. So again, we didn't get rid of the bottom. The bottom still has numbers down there. What we did is we got rid of the I part. There's no I in the bottom anymore. On the top, we do still have an I, right? So we still have the top has the I. The bottom just got rid of it. Okay, let's finish this off. Now, first off, the bottom, you can go ahead and add those, right? 4 plus 9, so you get 13. So you have 13 on the bottom. Top is still 10 minus 15i. And again, like I said, it's much better now because there's no I on the bottom. It doesn't look that much better right now. You're thinking, oh, it's still a big fraction, it's still division. Well, the trick here is now since we're dividing by a real number, now we can actually do it. We can actually take all these parts up here, we can divide by 13. Now, I say that, but 10 and 15 don't really divide by 13 nicely, do they? You can't say how many times 13 goes into 10, not with a nice number. You end up with a fraction or a decimal. So that's what we'll actually do. We'll actually say, well, 10 divided by 13 doesn't give you a nice number, so we'll just write it as 10 thirteenths. Same thing with 15 divided by 13. Doesn't divide nicely, so we'll just write it as 15 thirteenths. That's a fraction. It's 10 divided by 13, or it's a fraction. This one was negative, so we want a negative there. And the I will always put on the side. We talked about that earlier, right? Again, the I needs to be on the side. If you put the I on the top, my lab will count it wrong. I'm not picky on the test, so again, if you put the I on the top, that's okay. But on the my lab, you're going to want to put it on the side. So that's a good habit to be in. Now, this I would count wrong, because this is not in standard form. This is one big fraction. It's like you haven't even done the division yet. Yeah, you turned it into a division by a real number, but the last thing you should do is actually do the division and say 10 divided by 13 is 10 thirteenths, 15 divided by 13 is 15 thirteenths, and call this done. Now, I still kind of a little cop-out to say that's doing division because we left it as fractions, which kind of are divisions. But because we divided both parts, we're going to call that good enough. We have the real part, we have the imaginary part. That's going to be our final answer. So that's the best we will typically be able to do with dividing complex numbers. A lot of times we're going to end up with fractions. That's just going to happen a lot. So you're kind of stuck with that. But again, the idea, if you're dividing complex numbers, you don't divide, you actually multiply by the conjugate. So it comes to the test. Just to show you work portion of the test. I will definitely give you credit for partial work. And so one of the things you can definitely get some credit for is just knowing that when you have a division like this, you multiply by the conjugate. Even if you mess up the multiplication or don't get the final version of the answer, maybe put it like that, you can still get a lot of points for showing that you know how to do this first step. So make sure you remember when you're dividing complex numbers, you multiply by the conjugate to get your results. So you multiply by the conjugate and then simplify until you get your answer in that A plus BI form, real part, imaginary part. Okay, I'm going to do a couple more division problems, and that's this whole section. It's just mostly introducing these complex numbers and then how to add, subtract, and divide. So let's do one more nice division problem, and then I'm going to show you one simplifying problem that kind of will help out for later sections. So let's divide this one. Again, first thing is we want to multiply by the conjugate of the bottom. We're never multiplying by the conjugate of the top. So this one, there is a conjugate of the top, right? But we don't care about it. We only care about the conjugate of the bottom. So conjugate of the denominator. And again, denominator down is bottom. So we're going to take and we're going to multiply by 2 plus 4i. Again, we leave the first number alone. We don't mess with that. We only change the sign in the middle. So that's what we're multiplying by. We're doing it to the bottom, and we're doing it to the top. We have to multiply by the same value on top and bottom. And that way it'll keep the fraction true. It won't mess it up. Okay, so on the top, we're going to go ahead and we're going to have to FOIL both of these. So on the top, we're going to do 2 times 2, and we get 4. On the bottom, we get 2 times 4i, so we get 8i. So, oops, wrong pen. 8i. And then we do outside, so we do inner. 5 times 2i is 10i. And then we do last. 5i times 4i is 20i. We get 20i. Bottom, we do the same thing. So first, 2 times 2 is 4. Outer, 2 times 4i is positive 8i. Inner, so negative 4 times 2 gives me negative 8i. And last, negative 4 times positive 4 is a negative 16i. I times I is I squared. Okay, so we get that. Then we simplify. So the i's, the 8i and the negative 8i cancel. The top here, we can combine those terms. 8i plus 10i gives me 18i. So I get 18i in the top. Oh, I forgot. My 5i times 4i, I made a mistake. This is supposed to be 20i squared. I forgot to multiply my i's. I'm glad I caught it here. I kind of caught it because usually when you multiply these, you should have an I squared on every part, right? So when I do a FOIL with complex numbers, you should have an I squared, and that's how I knew I messed up. Okay, I got I squared, and again, I squared turns this into a negative, so this becomes a negative 20. Don't forget the 4 in the front. On the bottom, 4 stays in the front, and then the 16i squared turns into a positive 16. Because again, the I squared changes the sign. On the top here, 4 plus a negative 20, I can combine those like terms. 4 minus 20 is negative 16, still plus 18i. On the bottom, 4 plus 16 is 20. Now here's where, again, I take this and I say I'm not done yet because I want to divide both parts by 20. So I'm going to break this up so it becomes negative 16 over 20, fraction, because 20 doesn't go into 16 evenly, plus 18 over 20. Now one of the reasons why we like to write it this way is because once you get it like this, where it's 2 separate fractions, a lot of times you can simplify, right? When it's a big fraction like this, it's kind of hard to simplify. So here you can actually see that you can simplify both these. You can take 16 and 20 and divide them both by 4, right? Divide that by 4, you get 4. Divide that by 4, you get 5. So this becomes negative 4/5 if you simplify that one. Over here, 18 and 20 both divide by 2, so this becomes 9, and that becomes 10. So you end up with negative 4/5 plus 9/10 I. And that's going to be probably the best way to answer that. Now you might end up with like a multiple choice question or something that might read it like this if you're doing either the homework or the test. And that's okay if that's a multiple choice answer, that would be correct. I wouldn't count that against you. On the show your work portion of the test, I would want this for my answer. This is simplified because the fractions are simplified. If you're doing fill in the blank on my lab, this would probably be the best answer because again, you simplified your fractions. It's always good to simplify your fractions. That's why this would be the best answer. Okay, that's it for division. So division, again, you multiply by the conjugate of the denominator. That's what we're doing with these. So multiply by the conjugate, end up doing a bunch of foiling, and then you simplify a bunch, and then again you write, so you take both parts divided by the bottom number to get your final answer. Sometimes how we simplify. Okay, last thing I want to show you. So this one, notice, I think there's a couple problems like this in the homework, and this is actually something that will come up later in the homework, so I wanted to kind of show you an example of it so you're ready for it as it comes up. This is where I'm taking 2 expressions. They've got x's in them, so I'm not going to be able to solve and get like a nice final answer, but I can simplify it by kind of multiplying this out. Now this one gets a little tricky, so there's kind of 2 different ways to approach this. I think the easier way is actually not to use FOIL, because you can use FOIL for this if you're trying to think of that as one part and that as one part, but this is kind of weird to think of as one part. You can do FOIL, but I actually like the box method, so I'm going to show you the box method. And the box method is great when you're multiplying stuff with more parts. So first off, I'm going to get rid of this parentheses. So I'm going to go ahead and turn this into a plus, because if I do that, I can distribute the negative and change these signs, and now those parentheses go away. I'm going to do the same thing here. I'm going to turn this into a plus and change the signs here, and that makes the parentheses go away. So that's one thing. If you have a minus in front of parentheses, you're going to distribute. Now I have x minus 2 plus 3i, and x plus, or sorry, minus 2 again, minus 2 minus 3i. Goes plus and negative is still minus. And then this thing has 1, 2, 3 parts and 1, 2, 3 parts. And so the box method is a way to multiply if you have more than just 2 and 2. Most people know FOIL method because they're used to doing 2 by 2. For things with 3 by 3, it's actually easy to use a box method. The box method, what you do, you count the number of parts. So here I have a 3 by 3. And you're going to multiply using a box that's that many spaces. So you have a 3 wide and a 3 high. So I'm going to make a box. This could be 3 rows and 3 columns. So it's 3 by 3. And then I'm going to write my first, I guess it doesn't really matter if you do left or right. So I'm going to do the first on the, left or top. I'm going to do the first on the left, x, -2, 3i. I'm going to do this part on the top. So I'm going to do x -2 minus 3i. And then the multiply with box method, you take the row and the column parts and you multiply those together. So to fill this box in, I'm going to do x times x, and I get x squared. Fill this one in, I'm going to do -2 times x, so I get minus 2x. Fill this one in, I'm going to do -3i times x, so I get -3i x. Next row, now I'm on the -2 times x, -2 times x, -2x. -2 times -2 is positive 4, and -2 times -3 is positive 6i. 3 times 2 is 6. Next one down here, I got x times 3i is 3ix. -2 times 3i is -6i. -3i times 3i, well, -3 times 3 is 9, -9, and I times I is I squared. Okay, and then all these parts are part of your answer, but some of these will combine. And the nice thing about box method, a lot of times you can look down the diagonals, so you notice like these guys match, these guys match. Actually, this guy and this guy match. There's a connection there. So I can kind of put some of those parts together. So I can do x squared, nothing matches that, so I'm going to write the x squared down. I've got -2x and -2x, that's going to be -4x. I've got -3ix and positive 3ix, so those ones actually cancel because they're opposites. Over here I've got positive 6 and -6i, those are opposites, they cancel. So I'm left with 4, so positive 4, and then -9i squared, so I'm going to get minus 9i squared. I squared, notice, again, I squared is -1. So I can rewrite this as plus 9. So we've got 4 plus 9 with a -4x and an x squared. And now, since these are both just nice whole numbers, real numbers, I can add those together. 4 plus 9 get 13. So my final answer to this is going to be x squared minus 4x plus 13. It's going to look like that. That's my answer. So again, we didn't get a nice number answer, because we had x's in here. We got an expression with x's, and that's kind of what you expect when you start with x's. They're not just going to disappear. The i's did disappear because these guys were kind of conjugates. These guys were kind of opposites. One had a minus, one had a plus. But that's the idea. So I just wanted to get ready for these. If there's going to be a problem like this in the homework, but we'll actually see this come up later in this unit. So that's why we're seeing it here. It's kind of a preparatory. So this problem would be one I would probably throw in the test per se, but it's something you'll see in the homework a little bit later in other problems we do. So the problems I'd probably look at for the test would be like these division problems or these multiplication problems. You definitely want to be ready for those kind of problems, multiplication or division that we did, where we used a lot of foiling, that kind of stuff. That should be something you should be ready for the exam. And that's it for our first outcome. We started with complex numbers. One of the reasons, I'll just give you a teaser for the next set, we started with complex numbers because when we get to the second outcome for this unit, we're going to solve problems, and some of the answers sometimes will be complex numbers. So we're going to see this show up in this next section. We'll actually see it show up kind of throughout this unit. We'll solve problems, and some of the answers will be complex numbers. So I'm going to be done with that, and I'll see you on the next set.